Alright, so this is our dynamometer project. My name is Enrique.
My name's Isaac.
And for a formal introduction and background of our project, we knew that with the use of a potentiometer, it was possible to adjust the variable speed of our motor. We also knew that by attaching a Prony brake to the shaft, we would be able to calculate a force using a load cell, which in turn would give us torque and power. Uh, In addition, an encoder was utilized to figure out the RPM of the motor.
This is how we calibrated our load cell. So in order to calibrate it, we had a gram scale and placed basically a test weight. That test weight was my tape measure at 65.9 grams. At least that was the reading on the gram scale. We went back and forth between the gram scale and the load cell in order to make sure that it's working properly. After all the calibration was done, we got a percent difference of 0.448% between the load cell and the gram scale. For the calibration of the encoder, we got ourselves a 600 pulse per revolution encoder. That's a lot of pulses, so in order to reduce that to the Arduino, we got a 3-to-1 pulley ratio, as well as the max speed of the encoder can only have 6,000 RPM, so we actually had to reduce it because our motor goes up to 12,000. In order to calibrate it, we used a tachometer sticker on the pulley. We painted the pulley black and put the sticker on there so it's only reflective things showing. From there, the tachometer was just referencing that sticker. So we tuned it to a point where we got at 0.2% difference between the reading on the tachometer and the encoder. For the design, mechanically speaking, it's pretty simple. We can have a 4-inch arm that connects to a 8mm shaft. That shaft is connected, or at least grounded, to the plate by using 2 pillow block bearings. The pillow block bearings sit on pillow block stands. And the reason why we have those there is because we want the arm to be parallel with the surface of the load cell. So that way we're getting perfect tangential force on an arm. Now the shaft is connected to the motor by a coupling and to the pulley by a 22 pulley. The stand, the encoder stand, the pillow block bearing stand, and the arm are all made from resin, and everything else is off the shelf. Here is the experimental setup. Bottom left is the mechanical setup that I explained earlier. The mechanical setup is attached to the encoder by Arduino Mega, and the LCD display also attaches to that same Arduino Mega. The power supply that connects to the motor is 12 volts 30 amps with a DC power controller that controls the voltage to the motor, and that controls from 0 to 12 volts. Here is a video of the device working. Existence of its original living body inside the gate. Alphonse recalls by So here's our bill of materials. Net cost was $98.87. What saved us in this project was the amount of stuff we had on hand. So we had the Mega bearings, power supply, DC power controller, terminal blocks, and pulleys, all from previous projects at school. The biggest item we did have to buy was wood. We had to buy a planer wood, and the reason for that is because we don't want the load cell and the arm to be out of parallel. Then following that would be the encoder, the coupling, the motor, the load sensor, and the display.
So in conclusion, our Prony brake dynamometer abided by the price point set for this project. The RPM output displayed on our LCD was accurate. As mentioned, we compared this output to the digital tachometer. In turn, we got accurate results for the power produced by the motor, and we were able to display the results while actively adjusting the speed of the motor. And these are our references.